So, good morning. Today, we will discuss about furnace irregularities and its remedies. In blast furnace iron making process, as we all know that it is a concurrent reactor where the burden will travel from top to the bottom, and the preheated air the, that will be uh, purged into the blast furnace from the bottom to the tiers, and that will travel to the upwards. So this is a countercurrent reaction when the burden and the combusted air, the preheated air, when it is comes in contact with the coke which is present in front of the tuyeres, the combustion takes place, and the reducing gases will generate, and these reducing gases, especially of CO and CO2 in nature, so these will travel upwards and they interact with the solid burden, and that is how the solid-state reduction reaction takes place at the top part of the blast furnace, followed by melting, and melting process takes place inside the blast furnace. So during the process of the reduction of iron, followed by the melting, there are some irregularities which the operators encounters on day-to-day basis. So we will be discussing some of the irregularities which come across during the iron making process in the blast furnace route. So the first thing is the channeling. Basically, in the name itself, it is clear that the reducing gases are traveling inside the blast furnace in the form of channels, in the form of a preferential flow. Usually, the gases will travel inside the blast furnace both from the periphery as well as from the center. The peripheral flow will be there as well as central flow will be there. But whenever the gases encounter resistance to its flow in the upward direction because of the solid burden or because of the liquid products which are formed, then certainly these gases will prefer to flow in areas where it has a lower resistance to its flow. So that is nothing but the channeling. So because of the preferential flow, there will be an uneven gas distribution basically. Because of which the reduction reactions will not take place uniformly throughout the horizontal cross section of the blast furnace, and because of which there will be a temperature gradient also will occur within the horizontal cross section of the blast furnace. So the one of the reason for this channeling is the generation of the fines inside the blast furnace. As we all know that the burden basically consisting of different kinds of raw materials with different sizes and shapes. So when all these raw material travel together as a mixed bed of solids, inside the blast furnace, then certainly there will be some force formation takes place. There's a permeable bed will form actually inside the blast furnace. And if the mechanical properties of these raw materials are not good, then certainly it may generate fines during its motion inside the blast furnace. So these fines which are generated will occupy these pores and it will block the passage of the reducing gases as well as in reducing gases in upward direction, as well as the passage of the liquid products which are formed inside the blast furnace at the lower part also will be encounter resistance to its flow in the downward direction. So during that case, when the gases are unable to travel in the upward direction in one particular area, then certainly the gas will rise to flow with greater velocities. In that case, there will be possibility that fluidization may take place. That means the upliftment of the burden or the liquid products into the blast furnace takes place. So, because of the high resistance which are offering by these gases in the upward direction, the gases try to choose the path where it has its low resistance to its flow. So that is nothing but the channeling. So means instead of uniformly flowing across the horizontal cross section, rather it will flow only in one particular direction. Either it can be a peripheral flow or it can be a central flow. Okay. So this is called as. So how can we detect this channeling inside the blast furnace? Suppose inside the blast furnace during its running condition, if channeling has occurred, then how can we identify that the channeling has occurred inside the blast furnace? See, one indication is that there will be a sharp rise in the peripheral gas temperature in the neighborhood of the. So, as we all know that inside the blast furnace, there will be thermocouples will be arranged in different parts of the blast furnace across its height. So, through which we can identify what is the thermal profile of the blast furnace. So, if there is an abrupt change in the gas temperature at a particular area, so that gives an indication that there is a possibility of channeling has occurred. Other one is there will be a sharp fall in the CO2 content of the top gas. This is because, see, whenever these reducing gases, especially the the CO gas is highly stable at high temperatures in front of the tears, and this CO gas, when it travels upwards, when it reaches to low temperature, it loses its stability and readily it will react with iron-bearing material and tries to transform into CO2. So this CO to CO2 transformation takes place when there is a very good interaction between the solid and the gas. That is gas-solid interaction. That is, whenever there is a very good solid reduction reaction takes place inside the blast furnace, then the volume of the CO2 generation will be more. That will happen when there is a good permeability in the bed. That means when the gases are flowing uniformly toward the cross section of the blast furnace. When there is a high resistance which are encountering by these gases, then certainly a part of the reducing gas will not participate in the solid state reduction reaction, because of which the CO, whatever it is generated at the bottommost part of the blast furnace, that will simply leaves out from the blast furnace in the form of CO only rather than in the form of CO2. So that's why, because of it, a downfall of CO2 percentage in the off gas. So that is also one of the indication that if the CO2 content in the off gases is very, very less, then that shows that there is a problem. That means the gas solid interactions are not taking place properly inside the blast furnace. Then high flue dust losses. So if a huge amount of fines are generated inside the blast furnace, certainly these fines will settle down at the pores which are formed between the solid burden. And when these gases are rise to flow up with high velocity, certainly these fines will be pushed up, will be um, that is in the form of flooding. It will just push up, so that will joins in the off gas. So if a huge amount of dust is joining in the off gases, that means there is a loss in the permeability of the bed inside the blast furnace. Then drop in the blast pressure. Yeah, if there is a high resistance to the gas flow, then the pressure drop will be uh, the very high pressure drop will be there. So these are some of the indications for the formation of channeling inside the blast furnace. And what is the remedy is, the only thing what we need to take into the consideration is that raw material, whatever we are charging, that should have a very good physical properties. It should not, even though if you take a good amount of care about its property, but a certain amount of fine generation is possible, that which we cannot be avoid. But make sure that percentage of fines formation inside the blast furnace should be as low as possible. Okay, so that's why whenever we prepare any raw material, we check the properties of this raw material by doing some testings, whether it is having good strength or not. Um, uh, so we should make sure that generation of fines through this raw material should be as low as possible. That is one of the remedy to avoid channel formation inside the blast furnace. And also its distribution. The distribution of the burden inside the blast furnace also should be uniform. Then there will be uniform permeability in the bed of solids. Then the flow also will be uniform from the center to the periphery blast furnace. The next defect is the scaffolding. Scaffoldings are nothing but solid projections which are formed inside the blast furnace in the form of build-ups. Okay. So these are the solid projections which are formed inside the blast furnace, um, sticking to the walls of the furnace and um, encroaching towards the center, from the wall towards the center. So something like this. Yeah, these are the solid projections which you can see. Like this, there will be uh, these projections can be much more bigger also. Uh, there are two types of this kind of accretion formation may take place inside the blast furnace. One is at the top part of the blast furnace in the shaft region, and other uh, can be at the belly boss region of the blast furnace. Okay. Uh, the solid projections which are formed at the shaft part of the blast furnace are called as scaffolds, whereas which are formed at the belly boss region of the blast furnace are called as scabs. The reason for the formation of these kind of solid projections at a different part of the blast furnace is different from each other. Uh, the scaffold formation is at the top part of the blast furnace in the shaft region due to because of um, formation of high volume of alkali vapors inside the blast furnace. So from the burden, some of the alkali content will enter into the blast along with the raw material. So these alkali content, when it is enter into the high temperature zone, certainly it will convert into vapor, and these vapors will travel from bottom to the top, and at low temperatures it got condensed and stick to the walls of the furnace, and that will act as a sticky nature. So when the burden is traveling from top to the bottom, the burden which is located at the peripheral region of the blast furnace may stick to these condensed vapors, because of these condensed vapors, and that will form this kind of solid accretion. So as the burden is keep on moving, a part of it may form a layer by layer on this, and these projections may extend it towards the center of the blast furnace, because of which the burden movement will be interrupted. There won't be any uniform burden movement will be there, and also from the bottom, whatever the reducing gases which are traveling, those also will not come in contact with this burden which is overlain above these solid accretions. And also the temperature profile also will vary from the periphery towards the center. And the next one is the scabs, which are formed at the belly boss region. This is due to because of these solid projections which are forming at the lower part of the blast furnace is due to because of solidification of the slag. So during the fluidization, uh, the some of the when there is a high resistance to the flow of the gases, then um, the gases are allowed to flow in upward direction with high velocities. At that time, the flooding may take place. That means the liquid products may uplift in the upward direction, because of which when these liquid products travels into low temperature region, it may get solidified to the walls of the furnace, and that will form a solid projection. Those are called as scabs. Again, the consequences of formation of these kind of solid projections is also very much similar to that of what happened in the scaffolds. So the formation of these kind of solid projections certainly will interrupt the flow of the gases, flow of the solid burden, as well as it will disturb the thermal profile of the blast furnace and all. And how can we identify this formation of these scaffolds? One method of identification is that there is sudden increase in flue dust emissions by 100 to 200% or even more. Another thing is there may be an increase in high top gas temperature because of the solid projections that are forming. The temperature which is the heat which is associated with that gases will not be utilized by the solid, because of which there may be high top gas temperature may appear. And then lower gas temperature above the scaffolds with low in wall temperature in the neighborhood of the scaffolds. So as I already discussed that temperature from the periphery towards the center. Wherever there is a good flow of gas is there the temperature will be higher. Wherever there is a high resistance to the flow of gases there, at that region the temperature will be low. Similarly, CO by CO2 ratio in the top gas means there is no proper utilization of CO by the solid burden. That is, the solid reduction reactions are not happening properly inside the blast furnace. Similarly, the other indication is hangings, slippings, and non-uniform burden design. So these hangings and slippings are also the irregularities of the blast. Because as the solid projections are formed inside the blast furnace like this, if it is little much larger, then whatever the burden which is above it, that will be in hanging condition, that will never travel downwards, and that accumulation is keep on increasing. And as the accumulation is keep on increasing above this aggregation, at one point of time, the solid aggregation, whatever it is formed, that will not bear the overload which is above it. So all of a sudden it will get detached from this furnace wall, and that is nothing but the slipping. So that is nothing but slipping, and these detached accretions, whatever are generating, that will come and fall directly into the hearth part of the blast furnace, and that will create a chilling effect in the hearth part. So that will again disturbs the thermal profile of the liquid products inside the blast furnace. And because of this kind of solid projection, certainly there will be a non-uniformity in the burden movement inside the blast furnace. Yeah. So the remedy for this is how to avoid the formation of these solid accretions inside the blast furnace. You see, one thing is that the reason for the formation of accretion is there is the alkali vapors which are generated inside the blast furnace. So we have to make sure that before charging the raw material inside the blast furnace, have to see that the alkali content of the burden should be as low as possible, so that when it enters into the blast furnace, the generation of vapors will be less. And also, we have to make sure that the kind of the refractory bricks which we are using, the texture of the refractory bricks, what we are using at shaft part of the blast furnace, you see, it should have a very low porosity. If you have high porosity, the problem is that these vapors will go and trap, sit in the uh, refractory, sit on the refractory lining, and that may also lead formation of some low temperature phases, and um, in the due course of time, the refractory bricks also will failure, will break. So we have to make sure that these refractory bricks, whatever we are using, that should have a very low porosity, very, very low. And also, the concentration of these alkali metals, to decrease the concentration of alkali metals in the temperature range of 800 to 1100 degrees uh, by increasing their mm, exit in the slag. This can be achieved by decreasing the activity coefficient of alkali vapors, alkali oxides, by lowering the acidity of the slag. However, the acidity can be lowered below a certain limit in view of your desulfurization, uh, unless external desulfurization is available. And the second thing is control by flame temperature. The recirculating load of this alkali at 800 to 1100 degrees centigrade increases with increasing the flame temperature, and it is emphasized by the fact that the high temperature, the high flame temperature certainly produces high silicon content, so which increases the basicity of the post slag. So lowered flame temperature decreases the alkali buildup and facilitates its removal through the slag. But on the other hand, it increases the coke rate. So this alkali vapor formation, it is a cyclic process inside the blast furnace. And as I already said, that the refractory bricks, what we are using, it should have a high bulk density and it should be very compact, so that these vapors will not accumulate and stick to the walls of the refractory bricks. As I said, the scabs which are formed at the lower part of the blast furnace. The main cause is a sudden lowering of the slag fusion zone and increasing the slag viscosity and resolidification of the slag. As I already told you that when this flooding takes place, the liquid product which travels upwards, uh, they are basically um, uplifted forcefully to the low temperature region because of this solidification takes place. And the remedy is that charging of extra coke for melting down the accumulation. So wherever you have this kind of solid projections, make sure that at least in the next turn, whenever you are doing charging, uh, charge a little more amount of coke at that particular area, so that these accumulations will be reduced because of formation of high. If the hanging of the furnace is severe due to the formation of this kind of projections toward the center of the furnace, checking of the furnace may be necessary, and this reduces the beyond effect of the blast, and the weight of the stock column would break the accumulation. So we can change the burden distribution so that we can avoid the formation of these kind of solid projections inside the blast furnace. Charging of limestone away from the periphery to avoid formation of limey slag on the walls. This can be achieved by following this kind of a pattern, OO, that is ore, and then coke, and then lime and coke. So like this, or you can also use this kind of pattern, uh, two, two chargings of coke and one charging of lime, then coke, then ore and ore. If we follow this kind of pattern also, then we can avoid the formation of this kind of solid projections in the lower part of the platform. And then the next irregularity is hanging. It is basically the after effect of this kind of solid projection. As I already discussed in the previous slide, that hangings as well as the clippings. Okay, so these all are the after effects of formation of this kind of solid projections inside the blast furnace. So if ununiform descent of the burden in the furnace is if uniform descent of the burden in the furnace is interrupted by scaffolds, then pattern it is known as hanging. So that is due to the cause of maybe of fused slag or deposition of large amount of carbon in the voids that decrease the permeability of the burden and formation of alkali vapors. So these are some of the reasons. And remedies is you should add limestone of large size. Certainly, because dissociation, it will form CO2. The ACO3 dissociation takes place somewhere at around 1000 to 1100 degrees centigrade, which is actually a endothermic reaction. So it absorbs that heat. And this will lead to formation of a solution loss reaction to take place, and that will improve the probability of effect. And also reduction in blast pressure distributes the gas flow slowly but more uniformly. So this is one of the another. The next thing is the pillaring. Is another defect which is happening in the central part of the blast furnace. If the blast is unable to penetrate right up to the center of the furnace, so this may lead to the formation of cold central zone inside the blast furnace with an annular hot zone around it. So this is basically known as pillaring. So this we can identify it by inserting a bar to the furnace, to the tuyer pole. That will show a red hot portion at both ends and the cold middle portion at the center, if at all a pillaring is existed inside it. So the extent up to which you have a whole middle portion of the rod, so that will indicate the extent of pillaring inside the furnace. So the remedy can be increasing, can be eliminated, means the pillaring can be eliminated by increasing the blast pressure, which will penetrate more and will heat up the central column. So that is the only thing, to make sure that the blast will penetrate the center of the and we have to allow the burden to distribute in such a way that the blast will penetrate towards center. We'll stop it here. The rest of the irregularities we'll discuss in the next.